So I did a bunch of grading. I don't know if that's good or bad, but is this a bad? I normally make an assumption that you know if you turn stuff in or not. You kind of know if you, right? Since you have unit tests, you should kind of have a feel of where you are in the class, but the grading actually lets you know for real where you are in the class. So take a look at your grades. If something seems weird or a lab or an assignment, you think you did it, and I said you didn't do it or you got an error, but you don't think you got an error, just let me know and we'll try to get to the bottom of it. Otherwise, I'm going to probably grade assignment for today or tomorrow.
Perfect. I need 100% for my whole thing, so can we work on that?
Yeah, we can work that. Yeah. I accept bribes. No one's recording, right? I can say that.
Even if we are.
Yeah. But see, I accept bribes from everybody, so it's like equal opportunity, right? So that's the way it works.
You don't mention what kind of bribes either, so you know.
Yeah. Right, but I gotta treat everyone the same, so I accept bribes from everybody. I don't accept IOUs, no. That doesn't work. We have today's lecture 25. So we have today's lecture, Wednesday's lecture, Monday's lecture. So 3 lectures left. Only labs for today and Wednesday. So only 2 labs left. Lab 25, lab 26. There's no lab 27. And then we'll do a final test a week from Wednesday. Which seems crazy, but that's the end. Then we're done. That doesn't seem crazy to people. We've made it to the end. Right? And then that final test is not a final cumulative, right? It's final as in, what have we done? We've done templates, recursion, trees, and then we'll do inheritance and STL. So we'll do those 5 things. So nothing too bad, hopefully. The assignment 5, which is also due next Wednesday, is kind of like assignment 4, where you're going to take what you did in labs 23, 24, and 25 and convert them to a bigger assignment, which isn't too bad. I don't think overall. Hopefully you're seeing trees aren't as bad as linked lists. Maybe you think that, maybe not. Maybe it's just because, right, I was having this conversation with a student last week. It's like, one, it's recursion. So if you know if I give you the algorithm, it's easier to write than an iterative type algorithm, right? If you don't know the algorithm, recursion is actually really hard, right? But if I said, oh, output a tree in order, and you have to do it recursively, you might sit there for a long time before you figure out how that works. But if I say, oh, you just go left and you visit and you go right, you're like, oh, it makes perfect sense. So that's one reason why it's easier. The other reason why it's easier is just because now you've been working with pointers for like half a semester. Right? When we did linked lists, pointers were kind of new. Or really when you did assignment 3, right? Which I told you that was going to be the hardest assignment, right? It's because pointers were so fresh. It's like, oh, I don't understand what I use the arrow operator for. Right? When I use the star, what do I do? Right? And now hopefully you're a little bit more seasoned when it comes to this. Does that make sense? So today we're going to look at just one algorithm, which is the deletion algorithm. In order to run my version of the deletion algorithm, which is, once again, really inefficient, but really easy to write. Okay, everyone got that? It's inefficient, but easy to write. We're going to also work on the find smallest algorithm. So find smallest would be find the smallest value in your tree, because your tree is binary. It's also a search tree, so smaller values are on the left and larger values are on the right. So, right, where's the smallest value in the tree? What is the smallest value in this tree? 1. So 1's the smallest value. How do I know it's the smallest value?
Farthest to the left.
Farthest to the left, right? So you start at root, right? You go left. So long as you can go left, you go left as far as you can go. Once you can no longer go left, you're at the what? The smallest value in the tree. Does that make sense? Right? So it's actually a really easy recursive algorithm to write, right? We follow the left child until we hit what?
Left is null.
Right, left is null. So if the left, so this is the first time we run an if statement before you recurse. If the left, so if where you're at, right, get left child is null, then you're at the smallest value. Otherwise, you call the algorithm again and you pass in the left one. Right? So if, right, if I had find small, right, I would pass in a, what are we making? Oh yeah, BST node star sub, right? Remember, we're calling this the subroot, right? Because really the Feynman works for the whole thing, but it also works for, right, a subtree here and a subtree there and a subtree there. and then we do our check, right? If what? If, anyone know what I should write here? The algorithm says if the left is null, we are at the small. So how do I check to see if the left tree is null?
If sub arrow get left child is equivalent to
That makes sense? Right? Then we return where I'm at, right? Return sub contents, right? I think it's get contents, does that sound right?
yeah, that's right.
I try to mess it up just ever so slightly so when you copy my code, it doesn't work. Right? Nobody maybe understand what's going on? So we're saying if there is no left tree, right, then you're at the smallest value. There's one value in the tree, there's no left tree, you're at the smallest value, right? If that else, what do we return? We need to return it because we're returning the get contents, right? So we're going to return the same algorithm, which is what? Find small. And we pass in what?
Separate. Get left.
Right? If there is no left tree, right, get left child is a left tree, then we're at the smallest, right? Otherwise, we recurse. So we start at root, right? We start at root, right? Is there a left tree? Yes, so I call the same algorithm on this guy. Is there a left tree? Yes, so I call the same algorithm on this guy. Is there a left tree?
No.
No, so I return the value to this, which returns the value to that, right? As I pop things off the stack, which returns the value back out. That's why there's a return when I call my function. Does that make sense? I think I'm going to leave that code. I'm also going to give you the warning that I wrote a huge seg fault into my logic. So you can figure that out. Right? That's the Christmas present I give to you guys today. I gave you code that works minus a huge seg fault. So that sounds fun, right? And the hint is the seg fault is like the first thing that you'll get. So that might help you figure out what it's doing. Anyways, I'll let you think about that for a while. All right, now we get to delete. There's a reason why I'm only working on one algorithm today, and that's because delete has a lot of cases, all right, involved with it. Because in an array, when we delete something, and then we compact everything down. Everybody good with that? In a linked list, I delete one thing, and then I just update my arrows, right? And that's because both an array and linked list are linear, right? They have this before and after, right? So there's always a before, there's always an after. So if I remove something in the middle, I can just fix the befores and afters. Does that make sense? Trees, though, right? This is not a pun, but trees branch, right? We have a node has two children. I mean, not lots, but at least two children, right? So there are times where you delete a node, but that node was pointing to two children. You're not in a before and after, right? So the algorithm gets a little more complicated because how do I handle this, right? One arrow becomes two arrows. Does that make sense a little bit? Right? If I drew a tree over here, right, like this, 10 points to 5, points to 4, points to 3. That's not right. Points to 6, right? And then 10 points to 8. 8 points to 3. Or sorry, I wish I could make a real tree. Let's make that 12. Let's make that 15. All right, and all these guys point to null. All right, we have a lot of different places in our tree that we can delete. Okay, remember we talked about leaves and internal nodes, right? Leaves have no children, internal nodes have children. All right, hopefully you realize the easiest thing to delete is when you have what? No children, right? So if I was to delete 15, all I would have to do is get rid of it, right? And set it to what? To null, right? So delete it with no children, pretty easy, okay? Right? Let's bring it back though, because I need it for my next example. All right. So you can have no children, easy to delete. You can also have what?
At least one, right?
Right, at least one. So you can have children, all right, but there's some cases because you can have one child or you can have two children. Okay? One child also not too bad, right? If I was to delete 12, right, what do you think I should do?
Check to the left and right.
Right, point to 15. So I delete 12, right? If I get rid of that, I just need to take the subroot arrow and point it to the child. Okay? Now, that child is either going to point to the what? The left tree or the right tree, depending on where it was hung, right? Is it large or is it small? So there's some if statements in there. We'll go through it with our pseudocode. There's if statements in there to check to make sure, right, that we want to point it to the left tree or to the right tree. Okay? But the problem we have is when we want to delete 5. Okay? So if I want to get rid of 5, 5 has how many arrows coming into 5? 1. And how many arrows are coming out of 5? 2. Do we know how to make one arrow be 2 arrows? It's okay to say no. We don't know how to do that. We don't know how to take a single arrow, a single pointer, and all of a sudden say, actually, you should point to many things. Okay? And so we have to handle this case. If I get rid of this, right, where does 10 point? Because it can't point to 6 and 2 at the same time. Right? So we're going to handle that case, and we'll look at that in our code here. But we'll handle some of the other ones. Now, delete is also, remember we talked about search and destroy algorithms when we were talking about linked lists? So delete's also another search and destroy algorithm. Because if I say delete 5, what do I have to do first?
Find it.
Gotta find it, right? So it's find and delete at the same time, so we call those search and destroy. So we gotta find it, and then we gotta get rid of it. So we have to recurse in the tree. So actually we write a find algorithm, which finds where I want to delete, and then we write a delete algorithm. All right, so how do I find 7? The nice thing is we know what a binary tree looks like, right? So to find 7, where do I start? At root, okay? So at the root, right, what do I want to check for? If the value is greater than, less than, or equal to, right? Because if it's equal, then I found it. If it's greater than, which way do I go?
Left.
Sure, depending on which way you're right. If the value I'm looking for is greater, then I'll go to the right. You're saying if this node's bigger, I'll go to the left, yeah. All right. So if the value I'm looking for is greater, we go to the right. If the value we're looking for is smaller, we go to the left. Okay, but there's a big caveat, right? Because we're working with pointers. The first thing we should check for before we check for any of those 3 is null. Because, right, I say find 7, but what if I said find 100? Is it in the tree? So at some point I have to know to stop, right? I have to be like, okay, 100 is bigger than 8, 100 is bigger than 10, 100 is bigger than 14. I'm at null, which means what?
Stop.
You stop, not down. Right? So your first check would be to check to see if the root is null, right? The subroot is null. Right? Because if it is, then we can't find it. Because when your tree is first created, root points to where? Null. And can you dereference it? Can you say, is this contents equal to the thing I'm looking for? What happens when you dereference it? Segfault. Yeah, I heard segfault earlier today. Right? Those things might be related. Just saying. All right, but to find 7, right, I check here. Is the root null?
No.
No. Is 7 equal to 8?
No.
No. Is 7 smaller than 8?
Yes.
Yes. So we call the same algorithm, right, that I'm in, and I pass in the left child, right? Okay, left child. So now I'm here. Remember, every time I recurse, I run all the same steps over again. Is it null?
No.
No. Is it smaller? Or sorry, is it equal?
No.
Is it smaller?
No.
Is it bigger?
Yep.
All right, do it again. Is it null? Equal? Smaller? Bigger? Is it null?
No.
Is it equal? Yeah, so right? That's where I return. Or in this case, because it's search and destroy, I found where I want to delete, and now I have to run the deletion. Okay? Does that make sense? So it's 2 things, find and then that. So if the root is null, right, this is going through your if statements, right? If subroot equals null, right, you just return. Right, we're done. If the subroot's contents equals the thing you're trying to delete, right, run deletion. Right, if the value is larger, then call the same algorithm and pass in the right subtree. If it's smaller, call the same algorithm and pass in the left subtree. Does that make sense? Right, and that always will get where we want. So in this context, we're going to have a, right? We're going to have an if, right? We're going to have an else if, right? We're going to have another else if, and you can make it another else if, but I always think of it as just being the else, right? Because if it's not null, and it's not equal, and it's not greater than, it must be what? Has to be less than, right? Right. Now the key thing here is that the rest of what we're going to talk about today happens in that else if statement, right? Else if, right, equal, right? So this is null, this is equal, this is greater than, and then this would be your less than. Does that make sense? Everyone love my pseudocode? It's so great. This is find, right? Find the thing that I'm trying to delete. Either you didn't find it, so you can't delete. You found it, run deletion. It's greater than, go right, or it's less than, go left. Any more questions on that? That makes sense a little bit? Okay, now, the rest of what we're going to talk about today is once I found it, right, what do I do? And so it makes sense that I have 4 cases, but in deletion, I also have a bunch of cases, right? Because we were doing it on the board over there, what did we say? The thing I want to delete, the node has what? No children, 1 child, which can be what? Left or right, or it has what? 2 children, okay? And so while it's 3 cases, one of the cases has what? 2 subcases. So you write a 4-case if-else if statement, and then inside of this one you write a 4-case if-else statement. Does that make sense? Right? Because once you delete, right, we need to do some things. All right, so let's do the easy cases, and then we'll spend time on a hard case. All right? So we set all this. Yay, good. So if the node has no children, it's super easy. What do we do?
Just delete it.
Delete it and set subroot equal to null. Good, right? So if I get rid of 1, right, I first have to find it. Remember? Not null, not equal, it's smaller. Not null, not equal, it's what? Smaller. Now I found it, right? It's not null, it's equal. So I found it, right? And if it's no children, I just delete this and set subroot to what? Null. And that works because subroot is passed in by value or by reference?
Reference.
By reference, right? Which makes the arrow the same. That's the only way that it would work. If it was by value, it would have worked. Right? And if you're keeping track of like count, size, right, you should probably decrement that as well. All right, so to delete 1, I have to find it first, right? Make sense? So if I want to delete 1, we just went through those steps. Not null, less than. Not null, less than. Not null, right? Equal. Then we delete. That make sense? So the first one would be what? If, right? How do you know that it has no children?
You check the left and right child.
Right. So if the sub, right, get left child is what?
No.
And what else?
You gotta put an and, right?
Yeah, you gotta do both, right? And
The sub arrow get right child is no.
right, does that make sense? No children.
Then you just delete it.
Make sense? if, right, and where does this if statement go? It goes where? Where I have the black deletion algorithm, right? Because we have to find first. Once I found, then I can start writing my ifs. My edit ifs, sub ifs. All right, so that's no children. All right. What if it has one child? How do I know it has one child?
Would you just check both and put or? You just say
Check both and or.
you would just say sub arrow and then left and right child check to see if it's null or if it has a value.
So that's what we want to do, but we're not going to use an or, right? If, okay, let's look at, which one I want to, let's look at 14. Actually, let's look at 10, it's higher up. So if I was to delete 10, I'm checking, right? I just did a check. If the left child is null and the right child is null. That was false, right? Because the right child is not null, right? How am I going to figure out that there's only a child and it's on the right side?
If it's not null.
Right, left equals null and right does not equal null. Or the other way around, right? For the other child, right equals null, left equals null. Does that make sense? Right? Now I make my logic a little bit easier because I hate writing a bunch of ands, right? I'm gonna have to write ands for all this stuff. So I actually do the two children next. And I'll tell you why in a minute. How do I know that it has two children? The opposite of this, right? Where
If they're not
subroot
null.
get left child right does not equal null, and subroot get right child does not equal null. Right? So sub, I'm gonna go smaller. Get left child, right, doesn't equal null, and sub get right child doesn't equal null. Right? This is the hard one, right? Two children. Does that make sense? So you made sure that a node has, right, both are null, and you made sure both are not null, right? That's what I checked for, right? This makes my one child easier because I know that we're not in the no child case and we're not in the two child case. So in the one child case, right, now I can just look at one arrow because I know for sure, right, I'm not in the no child or two child case. Does that make sense? Like, if I'm here and I've already checked for two children and no children, I can just look at this arrow. If that's null, then it has to be right child, right? Or if this is here, right, it has to be right child. Or if this is not null, right, it has to be left child. I've already taken care of the two. If you write the check before you check for two children, it could be that it has two children, right? So, right, else, if, what? How do you want to check for a left child? How would we check for a left child? Right.
If the right child is null.
So, right, there you go. You guys said it both of the ways that you can check, right? Sub left child does not equal null, or sub right child equals null, right? Either or. I do a not equals null. Get left child doesn't equal null, right? Meaning there is a left child, right? One child, right? He's on the left, or she, right? Else if what? Sub get right child doesn't equal null, right? If there's something on the right, then there's a right child, right? One child.
You technically do that if check,
No.
just amazing.
You want to get rid of that? Is that what you're saying?
Yeah.
Because it's not two children, or it's not no children, it's not two child, and it's not on the left. It must be on the right. Yeah, I just gave a big long lecture about that. No, not really. Questions on those cases that I'm writing? Right? I haven't talked about deletion of two children or one child left or one child right. That's what I'm going to talk about now. But I wanted to set up our things. And that if else if statement goes inside of that else if statement. Boy, that looks like fun.
So we can't just write a function for the deletion algorithm. We have to just write it in that else if it's equal. So it's just
You could have a find algorithm, and in a deletion algorithm, you could call find, which could pass back by reference where you are in the tree.
Yeah.
But I'm not having you write that.
So we're just gonna have to write all that in that else if statement.
Yeah. For your assignment, I do have you write a finds function.
That's get, right?
Yeah. Right. For your lab today, you're gonna have this with that inside it. So we haven't written a lot of long functions in a while, right? All of our functions are pretty short. This one's actually gonna be fun. Which once again, that's why I'm taking a whole lecture to talk about one thing. All right, so if the node has one child, right? So I'm in this one child left or I'm in this one child right? I could be either of those, right? What do I do? If I was to delete 10, what would I do?
You'd have to just change the subroot to point to 14, right?
Right, okay. So I need to take the subroot. If I was to delete 10, I need to take the subroot and point it to 14. What's my problem?
Once you delete 10, you don't know where it is.
So I delete 10 first. I don't know where 14 and then 13, right, are. Does that make sense? So I just X out 10, right? All of a sudden 8 points to a non-existent place and 10's lost. So we don't have 14 and 13. So that's not good, right? If I take 8 and I point it to 14 because I know where 14 is because 10's still alive, right? What happens? 8 goes around 14, but what?
You don't know where 10 is.
I don't know where 10 is. So that's less of a memory leak.
And we need a temp.
Yeah, right? This is starting to sound like linked list, right? I think I've said this before. Right? This sounds very familiar, right? I need a temporary thing because I have to move some arrows and I still know where my original arrow was, right? And it makes sense because if you have one child, it is just a before and after type thing, right? 8, 10, 14, right? Linear. So we can apply our linked list deletion algorithm to it. Does that make sense? Right? Or if it was the other way, same thing, it's linear, right? When we have two children, then it gets non-linear. Right, so temporarily point to the node to be deleted, right? You need a temp that points to subroot, right? And then point subroot to the child, right? Subroot equals subroot get left child or get right child, right? That's going to change depending on if you're in the what? The left child case or the right child case. In the case of 10, right? Temp would point to 10, and then what? 8 would point to the right child because we're in a right child case. Does that make sense?
You delete temp, right?
Right, and then we would delete temp, right? And temp would go away.
You wouldn't even need to delete it, right? Because it would just, the function would end and it would just go away.
You would still need to delete temp, but not the pointer, right? Let's see if I can do this, right? Look, check this out. We haven't done this all semester. We can take temp, right? And we would point it to here, right? Look at that. Did you not know my arrows look just as bad on a computer screen? I have one of those cool pins, but I think it's in my office, so we're getting really bad. Okay, does that make sense? Temp pointer points to the same place that subroot. And remember, this here, I don't think this is going to work, but we're going to try anyways. Right? That subroot right there. Does that make sense? Right? And technically, we also have another subroot up here. Right? Because as I recurse down my tree, right, subroot comes with me. Right? The subroot becomes the next thing. Does that make sense a little bit? So 10 points to 10, right? Point the root to the child. So subroot equals subroot get left child, or subroot equals subroot get right child, okay? You have to say subroot equals, because that's the thing passed in by reference, but you can say subroot get left child, or you can also say what? Temp get left child, because temp and subroot point where?
The same place.
So you would say subroot equals subroot get left child, and so this arrow would lovingly point right down here. Right? Subroot equals subroot get right child. Does that make sense? And I know it's get right child because I'm in the one child right deletion algorithm. If it was a left child, right, I'd be in the one child left deletion algorithm. These two are exactly the same. Minus what? One of them says subroot equals subroot get left child, and one of them says subroot equals subroot get right child. So don't get messed up when you copy and paste that, right? Otherwise you're going to be deleting things that don't exist. Okay, so temporarily point that, and then delete temp. So we say delete temp, which means that 10 goes away. Okay, when the function ends, both subroot and temp pop off the stack. right? And then this subgroup pops off the stack. And then when you're done, 8, which pointed to 10, 8 now points to where? 14, which still points to 13. So one child is not that hard either, right? Because it's just, right, take this pointer and point it to the next child, whether it's the right child or the left child. And whenever we go home after this class, we'll be like, am I the right child? Or am I the not right child? Don't ask your parents that question. You don't want to know the answer. Questions on this one? We okay there? All right, and then, you ready for this? 2 children? How about we just like have memory leaks? That sounds good, right? Well, I can't delete a node if it has 2 children, so let's just pick one side or the other and call it. No, it can't work that way. So this is the complex case, right? And to figure out why my answer, my solution to the problem works the way it does, we have to talk about something about binary search trees or trees in general, all right? And that's the fact that the same set of values, okay, set of values, right? If I'm putting 1, 2, 3, and 4 in a tree, okay, a binary search tree can look different with the same set of values. Because for us right now, it's all about when I insert, all right? So these are all binary search trees. They all contain 5, 8, 7, and 9. They all are binary search trees, meaning that all the values to the root are smaller and all the values to the right are larger. Does that make sense? They're all trees. Right? But they look the same? No. Right? Because in this one, we inserted 5 first, and then we inserted what? 8 next, and then I inserted either 7 or 9, and those went where they were, right? In this tree, what did I insert first? 7, and then I inserted 5 or 8. But I had to insert 8 before I inserted what? 9. And this lovely tree, which is the linked list, right? This is a worst case scenario for us, right? We don't want our trees to look like this. We inserted 5, and then we inserted what? 7, and then we inserted 8, and then we inserted 9. Everyone good? They're all a binary search tree. They all contain the same set of values, but they are not the what? The same tree. Does that make sense? Okay? That's important because this means that I can kind of do whatever I want to my tree. I can make it look however I want, so long as all the values to the root are to the left are smaller and to the right are what? Larger. So long as my tree still has those properties, I can chop it off and move stuff around and do whatever I want to. Does that make sense? Because I could take this, right, and turn it into this if I wanted to. This becomes more efficient, right? This is less efficient. So I can take this and turn it into that. I still have a tree. And in fact, right, algorithms 3, doesn't that sound like so much fun? Take algorithms 3, you get to work on trees that balance themselves, meaning that they chop and move stuff around, right? Because you want your tree balanced, no more than 1 level difference between all of your children. Right? We're not writing that in ours, thank goodness. But, right, we can take this tree and make it more efficient. Does that make sense? That's important because I'm going to do some chopping in my tree, right, and moving stuff around, and so it won't look like the original tree, but it'll still be a binary search tree with the value removed. So, right, if I was going to take the first tree and turn it into the second tree, looks like I would take 7, right, and replace 5 with it, right? Put 7 in the place of 5, and then hang 5 off of 7. Does that make sense? Take 7, right, replace 5 with 7, and then I can hang 5 off to the left. Okay, now here's a great question. What is 7 in relation to 5?
It's greater than, right?
So it's greater than 5, good. What other relationship does it have with it? So 7 is bigger than 5, but what? Fill in the rest.
Is 5 also an ancestor of 7? Technically?
It is, okay, good. But if we're saying 7 is bigger than 5, right? What's the opposite of bigger?
Smaller.
Okay, so if 7 is bigger than 5, 7 is also smaller than what?
His child of 5's.
Say it louder.
8.
Okay, good. 7 is smaller than 8. It's also smaller than what? 9. So when we look at 7 in relationship to 5, 7 is the next largest value in the tree. Does that make sense? Okay. Meaning that when I took 7 and I moved it to the top, all the other values that were in that subtree are all to the right of 7. Because if 7 is the next largest value, right, these all values are always going to be what? Larger than it. Okay? Here's another way to say next largest value. Ready for this? 7 is the smallest value in the right subtree. Does that make sense? 7 is the smallest value in this right subtree. Can you say that a third time?
So wouldn't we just
7 is the smallest value in the right subtree. Meaning, okay, I hung 5 before. Let's say I want to get rid of 5 altogether. If I put 7 in place of 5, are all the other values going to be larger?
Yeah.
Because it's smaller than all other values in that tree, because it's the smallest value in the right subtree. Does that make sense? You remember the first algorithm I had you write today?
couldn't we just say get the right child instead on the find small?
Okay, yeah, find small, and we pass in the sub get right child. That's how we find the small. So we have an algorithm that finds the smallest value. Okay? And so for deletion, right, we're going to find the smallest value in the right subtree. So if I want to delete 5, I find the smallest value in the right subtree, which is what? 7. Okay? I bring 7, because we're just working with basic integers, I can just take the value 7 and replace 5 with 7. Does that make sense? So I'm not actually deleting 5, I'm overriding 5 with another value, because we're just working with basic integers. Okay? See, I don't know if I have a... Right? So basically we're going to what? We're going to find 7. We're going to do that. We're going to find 7. And then we're going to take 5, right, and make it be 7. Isn't that great? Right? Because if 5, everyone agree, I deleted 5, it no longer exists in my tree. Right? 7's in its place. Is 3 smaller than 7?
Yes.
Is 8 and 9 larger than 7?
Yes.
So is it still a binary search tree? Yes. Okay, what's my problem? I have a big problem.
Well, 7's still there, right?
Yeah, how many 7s do I have in my tree?
2.
I have 2 7s in my tree. Right? Remember, I called remove or delete, so I need to call delete on something, right? If I didn't delete this one because I just replaced it, which one do I need to delete?
7.
Okay, so here comes the big reveal, right? Do I know how to delete a value in a tree? Yeah, right? I just called the delete algorithm. Agreed? So I can delete 7 on the what? The right subtree. Okay, I'm here. If I delete 7 from the right subtree, it'll recurse down until it finds this, right? And it'll delete that. Okay.
Is this the case if there's 2 children?
This is the case when there's 2 children. Now, can this 7, can it have 2 children? Right, I remember I brought 7 back up. Can it have 2 children?
No,
Why not?
because you can't move it if it has 2 children.
So you're saying I can't move it because I have 2 children, but that's like just in good faith. Okay, so it's the smallest on the right. And we said if it's the smallest on the
It
right,
doesn't have children.
it doesn't have a what? Guaranteed it does not have a left child. Does that make sense? It could have a right child. But guess what? We know how to delete with 1 child, right? That's okay. It's only 2 children that's the problem. So guaranteed this one has no children, or maybe, right, it has a value hung to the right. That's okay, because 8 can point to that value. Does that make sense? So we call delete on the left child, and it runs the deletion algorithm again, and gets rid of 7. All right? And that's the fun thing about recursion is that we're in what algorithm right now? Delete. We recursed via delete. We hit 2 children, and now I basically recurse again, delete to delete the 1 child or no child one. Then we come back to where I am, and we pop back up. Remember I said it was inefficient? There's your inefficient.
So once you already write the delete algorithm, it'll just do it recursively?
Once you write it, it'll just do it, right? It's so nice. So called delete on the what? The right subtree. That sound good? Give you a little bonus time and lecture out today.
Complicated.
It is complicated, right? Hopefully it's find small, it's not too bad. Right? I think it's I think it's called find min for you or find smallest, something like that. Right? And then the other algorithm you have to write is what? Delete. Delete is made up of a search, and then in this case, it's made up of a what? Of a destroy. Okay? I gave you a lot of the logic for the cases, right? And then I gave you the pseudocode for the deletion. Okay? And so I think between those two things and maybe a little bit of help from me, you should be good. Unfortunately, you can't write lab 25 until you write lab what? 24. You can't write lab 24 until you write lab 20. 23 is super easy. Right? 24 is actually not too hard. People that have written the tree one, everyone agree they're not too bad? Right?
The first one's not bad.
The first one's not bad at all. The first one you could have written like 2 months ago. Right? The second one's not too bad. Sometimes it's just an ordering thing. But the nice thing is that if I come over to help you, it's not like, oh, all of this code is wrong. It's like, okay, just you're doing this in the wrong order. Let's just flip it on. Okay. Remember, everything's recursive. So if you write a loop, you're doing it wrong, right? You're doing it wrong. The loop is a recursion loop via function calls, right? How do I do the same steps over again? I don't write a loop. I instead call the same function with either the left child or the right child, which is why all my parameters, right, I call them subroot. To remind myself that I'm in a subtree, right? Which a subtree works the same as the parent tree, right? Trees are made up of subtrees. And they can be null, right? So get rid of your big old segfault in this algorithm too, right? And that's my warning. Big segfault in that one, and that's because it's what? Trees can be null. Yes.
I had a question over what you were just talking about, the two children. The algorithm. So we're deleting 7. Are we deleting 9 too?
No. So remember I was trying to delete 5, right? So I find the smallest value in the right subtree, so it recurses down. Oh yeah, there it is.
I think I was just thinking that we're trying to delete 8.
Everything. Oh yeah. So I was going to delete 8. Same algorithm would apply, right? Find the smallest value in the left subtree, 7. Remember, if there were more, it would go farther. But it finds 7, it copies it back here, right?
And that leaves 9 on the right as the right child.
And then we're all good. Actually, I think I did that backwards. If I was to delete 8, 9 gets copied up, not 7, sorry. Find the smallest value in the right subtree. So I go right. 9 has no left child, so it's the smallest. 9 comes up. And I delete 9 in the right subtree, which leads this. No children. Okay. It's kind of weird. All right, get cracking. 2 labs this week. Those are the last 2 labs you will write this semester, right? 1 assignment, last assignment 5, based on today's lab, basically. If you can get lab 25 done, you should be getting assignment 5 done as well. And then a final next week. Next week? Shoot, next week. We only meet 3 more times. Oh no, don't be sad. They'll be all we'll be okay. Other questions? you got before.
I tried, I don't know, 5 or 6 times on Saturday, and I got so frustrated, I just, I let it out. And I came in, opened
Yeah,
up,
that,
tried
this
it.
is totally different.
No issue.
Pass file pathway was not right. It's like,
All right, we're gonna put this on canvas, but we found out last week, if in your new code MD, so your Eclipse J, if there's a yellow triangle on the bottom, we need to fix that before you move to it. We've got a yellow triangle on the bottom. What it'll do is it actually gets rid of all your files every time, which is terrible.
I turned that off and it still got rid of all my files.
What?
I had to recode my workspace and it wouldn't let me recode it for all of Saturday. It said permission denied.
Permission denied?
Yeah, and then I came in this morning, tried it, it worked the first time, no problems.
I don't know, I'm cloning mine right now.
I don't understand it.
So what is it?
What? If your files are all gone, then there's a weird setting that we need to change.
I had to forward everything back.
So before I,
I lost everything for it's under
that's what I
four.
didn't do the last time.
And then going
I
like,
don't know if I can do it. I'm gonna be upset with it.
Make sure, but right, always make sure before you leave, you add and commit and push everything.
Yep, that was my fault. Whoops.
Last dot.
So that would be 25.
I just ran it.
That's great.
So do you need help on my forms where I can help you? Since I have mine committed, like committed it before that.
Yes. I might, don't quite remember.
Should I have any failures here? Are you still in passing segment?
Fineman, Fineman, the public one should have what you're trying to find. Oh, sorry, no, Fineman, yeah. Public one has nothing, this, the private one still needs to, so, we have it there.
Okay. Oh, I see, I just for the.
Yeah. Which, something, just like you're supposed to have done something in your output. Basically, got it. 420,000 bytes for every 2 times. It's 1 byte. That's crazy. I have your repository on my computer, right? So let me fix it online and then. Was that 11 that we're done now? good, right?
So that's in the workspace called PhD. Okay, so yeah, kind of. So this class is when I have contacts. Right, it's right on time. So then what I would look at the best practice. For templates. So here's the class. Notice that. This work is good here. You start defining it, right? The class was called simple, right? But now nobody's classing colon class name and then because all of a sudden you get some links, you get some bubbles, you have to do it on everything. So like this guy, right, exactly. So like this guy has to have your first one. It would have to be this. This would have to be. And then we're getting really crazy because this is the class, right? This is the type. And all these up here become the bracket. Because I can't do that. This still stays this. So the height. These are functions. They have to use the height. We use this one as a reference. So that's about it. Now every function, even if it doesn't use t in it, it still needs this because every function is a part of this templated class, so they all need to look at it. Just how much fun.
Thank you.
What? That's nowhere near. I had a full. Wow. I don't know what that was. I was just typing and all of a sudden just reset. Can you hear that?
I think I've had issues with I'm using my laptop. I'm bubbling the page and it just goes back to the top.
Dude, it's like it went through and deleted like 5 layers at a time. I'm redoing what it just made me do. I remember what was that either.
I hope that doesn't happen to me. Spend all this time just redoing the work I did for time 4. I have to do it all again. And like, last time I was working on this, having 4 functions and we just had to have a lot more.
I was just thinking, so I'm figuring out why I just.
If I'm modeling that, or some form, like it would be first, it was pretty much essentially like you take guns and levels.
No, because, well, I think remove had a remove first or whatever, we just removed the first.
There's not the same as you take guns.
No. I don't believe so. No, because those don't have to deal with like.
Which one left to this thing, sometimes it's forward, I'm not sure.
Yeah, that's just saying, basically you're just iterating your principal question, going through it and seeing if it ever, the case where the contents of the syllabus ever equal the past-name contents, and if the reading becomes true, that never occurs and you can't reach it at all. I've looked at them.
Also for the, hold on, the functions to string to try to add words. But also, just to do like what we did
I was sitting there typing away, and then this occurs. It just like erase everything and turn into that, and then none of that was there. I started pressing Control Z, and then it started doing this. Yeah, I don't know what that was. I'm gonna do the rest of my files.
Right. I think these just relate to these. So let's just say like they're, remember how like pre-compiles and looks at errors? That's what those are, but how to get it back to.
It may have popped up after it happened, I don't know. But
I don't do that.
oh, and it's like, it kept coming back like section at a time, like it would do like 6 of it, you know. It's like a deleted everything in small little chunks. It was already the most recent thing that typed in.
Right, yeah. Sure. Sometimes they have like a history thing.
First of all, just going, all of a sudden, just everything goes down to like 3 lines. And so
Oh, right, yeah, we can like.
I mean, I would just type that in and then it just went
Right, and then everything else went on. I'm not sure. No, I can come back to that.
I mean,
Yeah, I don't think there's gonna be anything that we could. Maybe try closing that.
well, that would be so screwed because I can't close this. When I drag it over there, yeah, I can expand it and whatever, but
Out of the work.
I try to pressure.
Right,
Your
yeah.
life work.
That's my buddy crew.
The interface looks a lot cooler, but it seems like it has more magnet buttons than the last one. It's not cool though. So what about you? Yeah, that's really good. This might take up like a minute or two. Just let me know what it says. This will say like
No, it said it's already running. I'm gonna try to get the computer maybe.
Okay. So let's see what happens.
Try doing online. Yeah, it's still same deal. One time has already started.
I wonder, yeah.
Now it's not even, like it just, it tries for like a second, and it's going to say that.
Yeah, I don't know. It's got what, like about 15 minutes before it like kills it on purpose kind of thing.
Yeah, it decided on you.
Yeah. So you could create a new workspace and then come, or you could wait.
But creating a new one means I'd be pulling everything off of GitHub, right?
Again, yeah, so you go back to whatever it was. Whereas this would at least, if you wait, should at least be whatever change you made to each file and then.
Pretty sure I was a significant amount typed into Simon 5 and it was never.
That's not what it got.
No, it wasn't. That's what I copied from.
So I'd probably wait 15 minutes.
What, Luke?
Yes.
We're already having problems with the clips.
Yeah.
Okay, what does this mean? When it references?
It just means the same thing, just return contents underscore.
That's it?
Does it?
Because I tried that and maybe I just didn't do it correctly.
Yeah, it is, but
Contents.
it's different from a link.
Yeah.
The stuff you're looking at is the
Okay.
link. I can just tell like how this is.
This one would be return left child.
Yeah.
Oh, I'm sorry.
It basically allows you to, so you get to use the accessors.
Yeah.
But if you return it by reference, it actually makes the assessor can also be a mutator because you get the value back by reference. So if you change it, then it'll change the value.
So, meaning that it kind of just becomes both in a sense?
Yeah, you could say get left child equals 5, right? And it actually
Yeah.
changed the thing.
Okay. Let me try that.
So it's your constructor. Maybe you
Yeah,
didn't set left and right to null.
My overloaded? Or is it this?
Both of them. So this one should set right child and left child to null.
Yeah, that should be like the default
Yeah.
inside the in the thing in the constructor or the parameter.
No. Just inside the function.
Oh, okay.
Just just
Okay.
left child equals null, right child equals null.
All right, thank you.
Hey. Wouldn't you like to know? Yeah, you don't want to do that again, do you? You make sure before you leave that you add and commit and push everything, just in case you just. Yeah, that would be easier.
Yeah, but I actually pushed mine right for you, so.
You're all good. Keep this so. I mean, you're like, what is this thing? That's just to name it as quickly as possible, so. Yeah, I wonder if it makes the change while it's running, if they'll actually lose everything until you start it. I guess through the triangle, but it's still a work in progress trying to figure out. Yeah, make sure before you leave today that you add commit and push. That way everything's at least back up together. Yeah. If anything weird happens, you're at least okay.
So I was just wondering, when I was looking at, the first part, the time form, how's that any different from, like the Untitled Algorithm?
It's not really.
It's not?
Well, you're still adding something to the front of the place, right?
So could I, am I still using the head variable or?
Well, you're using whatever you call them in the DL, so they're gonna be named in that's all this stuff. Yeah, you just need to have your and all that stuff. The only difference between what you did in your labs and your DL list is that you have pointers both directions.
Yeah.
Right, so when you add something to the front, right, in SL list, we said the first node, like this new node points forward to the old head. But now the old head also has to point backwards to the first one, right? You have to make sure that the links go both ways, right? So all your algorithms are going to need changes to them. Backwards.
So, could I, commercially copy and paste this code and just add like the back part?
I mean, you can try, but I want to copy and paste it because the names of everything's different. Right? All the functions, all the class names are all different. So you want to use that as your basis for sure. There you go. You just clone everything again?
Terrible. Terrible was I got rid of the triangle and I still had a clone.
Yeah, that's the terrible part. We're gonna find out on Wednesday, because now it's been off all week, right? So we'll find out.
I'll find out when I go home later.
Yeah.
That's true.
But I'm gonna make sure I push it before that.
That's all you do, right? We need to make sure. My time's already started, right? Oh, it's here. Oh, I see.
So it's basically.
control Wi-Fi, I'll do a hard refresh. So yeah, but I don't know if it's working. Oh wait, but at least it's not saying not working. It's saying loading. Good, I think.
Yeah, sometimes it takes a bit.
Yeah.
When I did my hard refresh on it, and then I went to go try to pull, and it's like loading.
But then it might work.
Yeah, took about 7 minutes.
There. One more week. Put up with it for one more week. That's all I ask. Then we can get rid of it.
Yeah, I think all these are extra credit for dealing with it.
You should get 200 points.
I'll extend the due dates to next Friday, next Thursday. Oh wait, that's when everything's due.
You know, if I wasn't a smart,
December 31st?
I would have been like, that sounds great.
I'll take it. Well, I can't trick you guys. You guys have been around a long time.
just gotta make it happen anymore with this.
Yeah, it doesn't work.
If you're not.
Yeah, I'll be around. I got meetings in the afternoon. Tomorrow's Tuesday. I mean, at 10:30, and then I mean at 2. So I'll be around. You can always text that number or email me. There's a number on the syllabus that you can text.
Oh, okay.
Fractions.
But all that does is just either.
Oh, I see.
But you can just do that. I remember how my phone up, so I'll see. Oh, this person wondering how I might get. Yeah, I'm around it. No, I'm in meeting.
Okay.
That kind of thing.
Okay, fine.
But I'll be around. If I'm not in my office, it's because I'm.
Oh, okay. So if you're not there, just shoot me another text.
Be like, hey, I'm at your office. You're not here. You're gonna be here soon, or did you just leave for a meeting? And I'd be like, yeah, I'm never coming back. Not for you. This isn't a not for anyone kind of thing. It's like, not for you, but I would come back for anyone else.
I'll just retext you with a different number.
Joe's at my office. Who's Joe?
You know that new student that hasn't shown up this whole time?
Yeah.
But I've been doing the work? Go.
Joe.
I'll picture this.
That only works so long, but as soon as I don't show up and do the work, it's like you see their work, and then all of a sudden, like at some point, it just like stops. Like, oh, they lost the will. It's hard.
Eclipse, whatever, it keeps on crashing.
Eclipse crashes or the browser crashes?
I think it's a browser, but I'm not sure.
Looks like a plugin.
So try, or what browser are you in?
Chrome.
Try Firefox. You don't want to crash.
It's so weird though. Never did that before.
Things never break, it doesn't break. That's how it works. Well, you're passing in, they all have like pointers, right? So you are passing pointers. Yeah, I mean, so like on insert, is that what you're saying? Or, yeah, so on insert, all that's being passed in is the value. So you're gonna create a node. Or, right, if the node already exists, you're just gonna account and not create it. So there's two possibilities on insert, right? Once you find where you insert, either you insert because it's null, right, and put it in system tree, or you found that it exists, and then you just need to make the current count. So you'll create a new node on one of the cases, but not on the other case. Does that make sense?
Yeah, if we're,
You are. You are. So you have the public. So you have the public answer. Private answer. Yeah. So it's gonna mirror what we did. Firefox crashes?
I said, I swear if it does.
If it does. If that's it. No more stuff to us this week. Yeah.
That the gods are telling me I'm not supposed to be able to summon.
Luke, are private functions defined in the H file or the CPP file?
Right now, CPP file.
Okay.
So you just put them in the private colon section of the H file, but then you define them.
Okay.
Hit F5 one more time and see what happens.
This is very unstable. This app.
Especially today.
Oh, it's because everyone's actually doing their work. It's the only reason why
You're the
we're.
only people. You're the only people that actually use this, and we're taking on this.
Well, you figure everybody had to do the big move to something.
Yeah, that's right. Yeah, on Sunday. Yeah, so today's the first day where everyone's on.
And it's a Monday, so you know everyone's showing up to work on Monday.
That's right.
Even though you don't want it. You ever notice how long this platform has been around? Since like.
Well, I mean, this is a Coach Che version 7. I don't know how long it's been.
Version 7.
I mean, Obi's just been around a long time. There is there AWS or whatnot.
But when I was looking up the whole quick stuff, it went back to like 2006 for like people complaining about their workstations disappearing.
You've been here a long time.
Why'd they get rid of Code Envy then?
Definitely not gonna work for you because nothing against programming, it's just.
No, there's nothing against it. It's all programming.
Yeah.
You get paid a lot for punching stuff that's already been written most of the time.
We're really good at copying.
Yeah. Whereas, hey, you forgot that one semicolon, do it all over again because we don't know where it's at anymore.
This is good.
Right. Never worked out in the fun. Just I thought you wanted to show up to do it for your breakfast.
Yeah.
And I got here and I was already here. I was like,
It's been like 7:40. You're kind of late, dude. Yes.
yeah, like my.
So I'm just gonna How do you type stuff? You like, it's like,
For 4 years, it's 1.5 minutes.
Yeah, it's all. But it might be because they shut themselves down after the 15 minutes, so it can be like 15 minutes of nothing. But by the time we do it today, we can check it and see if it's, because that'll be, you know, what I mean, that'll be a lot. But this will allow you to,
So this will allow you to use it. This will be your.
I mean, it might have online, but it's not. It was maybe really good at it, isn't that? Okay. You're almost there. Because you're putting the current where you are currently, right? Great. All that's missing is that this thing, right, is defined as being, right? Defined as being, that concept. Because the in-order function says it returns a string of all the values in that tree space separated. So when we call it on the left child, we get back a string of all the values in that subtree space separated. So that's just a string. That's like saying 10, 20, 30. That's what that means. So what I want to do with that. That's not going to do anything, right? That's just a value. What do we want to do with value? Where do I want to do that? What we have is a sort of bug. Where do that? This says, put into the string the whole left tree, right? Essentially. And then we put in where I currently am. And then we want to put in the whole right side tree space. Because of the recursion works, we're going with that one. That's it. So if you had run yours, you would have gotten just one value. It's not a previous value. Because we want to that. But now you are going to left. It's okay. You define in order as something based on the so then you call it the left side to be a space separated. The right
It's not really sure it's structural.
Which is why I was like, see that? See, there's no features in there.
Central Health. It's not much. This could be what you have to have it. We have to be. Well, I guess it's not. This one, I think it's supposed to return true or false.
Okay.
Alright, so it could be that really. And a lot of times students screw up because they return true, they return false. But when you, right, there's also two cases when you go down the right tree or the left tree, you can call the function. You have to change it in terms of. Because whatever value comes out of that function, you don't get it back.
Okay.
Yeah. So I don't know which one of those might be. Those are normally what we see.
Just a. Oh, I see.
Make sure that the things to the DL. You should just go to change the master.
I think I need to. Start that. And I have a student. I think they will help. usually, just not the first, when I'm sort of when last night is about the user using this stage is on type one. This I was just going to notice that I just didn't want to.
Yes. Yeah. So if you think about it from an outside perspective, the user that uses your tree doesn't want to know about pointers and all that stuff, right? It just wants to say insert 5 instead of going to tree. So that's why they call the public one, right? Then the public one calls the private one where you get a pass group underscore into it. Yeah. This one should just say return insert contents comment root underscore. And that's it. And then this will handle it. Yeah, so those yes go into it. Okay. All right.
So the next one. Because you're actually. So this is on the front. You're gonna basically all what you're passing in after you.
So,
So because you're passing in